So we're going to look at shapes of molecules, the ones that meet the octet rule. These are the simplest ones. We're going to look at in another video ones that do not meet the octet rule. But for now, we just want to get familiar with the most simple forms. So the first one we'll look at, the shape is diatomic. There's only two atoms. There is no central atom. So because there's no central atom, there is no regions of electron density around the central atom. So an example is oxygen. So here we see the bonding electrons are in a double bond to meet the octet rule. These are the non-bonding electrons that aren't shown on this particular model. But we really only care about the central atom. So if we look at the next one, linear, or sometimes called linear triatomic, there's two regions of electron density. As shown in the Lewis structure for carbon dioxide, these are both double bonds. So if I get a model that's a little bit more descriptive, I have the central atom, two regions of electron density. In this case, the outer atoms do not have their non-bonding electron pairs on them. Then, the next level of complication, complexity, is planar trigonal or trigonoplanar. So three regions of electron density, and you can see that this is trigonal right here, and it's planar. And if we start talking about bond angles here, there's 360 degrees in a circle divided into 1, 2, 3 equal pieces, makes each bond angle 120 degrees. So in our example here of nitrate, I'm going to use this model, and this shows you the three regions of electron density. One happens to be a double bond. Here we have the non-bonding electron pairs on the outer atoms, but they don't affect the shape. And the shape, of course, comes about because electron pairs repel electron pairs. That's why most molecules are symmetrical given the chance. So now the next one, if I take one of the atoms off of this, I get what's called the nitrite ion. So here I still have three regions of electron density around the central atom. So this is the non-bonding electron pair, which still takes up space on the central atom and repels these other atoms away. The bond angles would be slightly different than 120 degrees, but for our purposes we just say 120 degrees. And of course, another polyatomic ion, it doesn't matter, we apply these principles to ions or to molecules. So the bond angles between here and here is about 120 degrees. And then, finally, we have four regions of electron density, which is a tetrahedral shape. Tetrahedral means that there's four sides. So here's the one side on the bottom, 2, 3, and 4 sides. And as it turns out, the bond angles in a perfect tetrahedron are 109.5 degrees. So you can see this is greater than 90 degrees. And so an example here would be methane. So I have four regions of electron density. Now what if I take one of the atoms off? Now the shape is called pyramidal. Pyramidal because it has depth. It's not flat, it's not linear like this one, okay? And so the bond angles here are still approximately 109.5 degrees, but we call it pyramidal or trigonal pyramidal or something like that. Pyramidal is good enough. Now, if I were to take one more atom off, I still have four regions of electronegativity around the central atom. But the shape of this is bent. So when we look at this where the atoms are, we see that the atoms make a bent shape. In X-ray diffraction models, we see X-rays are diffracted by the atoms, not by the electron clouds. So what we see is bent. However, this bent is different than this bent. Whereas this bent is 120 degrees, this bent would be 109.5 degrees. So these are the basic shapes, and We'll do some more videos with this, but if you know this, it's a great start. You'll be really doing well.